So my name is Jinkun Zhang. I'm a PhD student at Northeastern University. Today I'm going to talk about a paper with Yuezhou and Edmund. Unfortunately, I cannot make to Torino due to some visa issues, but I hope you have a great time there. Okay, so the paper is titled Optimal Congestion-aware Routing and Offloading in Collaborative Edge Computing. So I'm sure you are all familiar with the concept of edge computing. But the collaborative edge computing, or CEC, is an extension idea of edge computing. It generally refers to any network where nodes can collaborate with each other and to finish computation jobs. So the concept of CEC is applicable in many practical situations like a smart house IoT network we're showing here. So the difference of CEC and EC is basically like, first, CEC has a flexible network structure. It doesn't have to be a layered or hierarchical network where you have cloud, edge servers, and users, and they are all distinct. Instead, the component of CEC network just be nodes and links. And second, the nodes and links can have heterogeneous capabilities in data generation, in computation, and in transmission. So with this flexible structure, we naturally ask a question: how to optimize the routing and offloading in CEC, namely where to place these computation jobs and how to deliver the data and the results of these jobs. So the problem of joint routing and offloading is widely studied in previous works under different assumptions. Here are some closely related ones. Now, some of these works have great results, but their assumptions is somehow limited in the sense that the topology of the network and the cost function may be limited. Now, however, in our paper, we use a novel and powerful analytical framework that achieves the following aspects. First, we allow arbitrary multi-hop network topology. It doesn't have to be a layered or mesh structure. Most of the previous work assumed one of these kind of specific structures. And second, we use a flexible task model. We allow multiple data sources for one task and allow the destination node to be distinct from the data source. Third, some of the previous work didn't account for the size of the results, while some of them did, but it's merely transmitted in the reverse path of the data. However, we separately optimize for the routing for both data and result, as well as the computation placement. And fourth, our model works with non-linear congestion-dependent costs. Most of the previous work just used linear cost, but in real network, right, when large traffic is going through the same link, the performance of this link could decrease. Now we will see later how we formulate congestion-dependent costs. And next, although our problem turns out to be non-convex, we're still able to solve it globally. And the solution leads to a distributed algorithm, which has the fast convergence, fast and guaranteed convergence, and the promising performance, especially in congestible networks. Okay, so let's start with the model. First, we have a network G with arbitrary topology. Here, V is the set of nodes and E is the set of links. And there are multiple computation tasks being performed in the network, and we use S to denote the set of tasks. Right, here are some basic assumptions of these tasks. First, we assume a flow model. Namely, the data is continuously input into the network and the computation is continuously performed. And both could be viewed as streams of steady rates. Right? This contrasts with many task scheduling works, where there a task is only performed once with some pre-given assignment time. And second, we assume that a task is divisible for partial offloading. Namely, the data and result can be divided and routed on multiple paths, and the computation can also be divided and partially performed at different nodes. Now here we give an example of a task. We assume there are two data sources at 1 and 2. They could be sensors. And the data collected from these sensors should be computed, and the results should be delivered to node 3. The data blocks and data packets arrive at the data sources and is routed in the network in the form of data flows. And the data flows is routed to some nodes to be computed. Like here we have node 4, 5, and 6. After computation, the data flows are converted into result flows, and these result flows are further routed to the destination. So basically, a task refers to this whole procedure to route data from data sources to the computation nodes, perform the computation, and then route the result to the destination. And what we want to optimize is how to route these data and result flows and where to place these computation nodes. Now we further assume that all computation performed in the network is of big M types, where each type refers to a kind of computation like matrix multiplication or image compression. We assume the data result size conversion ratio of type M is AM, right? Namely, the data flow of unit rate will generate result flow of rate AM. Typically, we have AM less than 1 if the result is smaller than the data, but we also allow large AM for special kind of computations like image super resolution. And we use a pair DM to denote a task. Here D is the destination node and M is the computation type. So here this task is denoted by 3M. And next we're going to quantify these amounts. Right? First we use RIDM for the data input rate of task DM at node I. For example, here we have R23M equals 4. This rate could be in bit per second, block per second, and etc. And we use F minus ij for the data rate on link ij. Right here, if you assume that half of the input data at node 2 is routed to node 6, then F26 minus equals 2. And we use GIDM for the data flow that is put into the computation at node I. And here we assume that all the data that arrives at node 6 is computed there, so G6 is also 2. And we assume AM equals 0.5, then the result flow we have from node 6 to node 3 is 0.5 times G6, which is 1. And this we denote as F plus ig. Right, next, we define T minus and T plus to be the total data flow rate and total result flow rate at node I. And we define phi ij minus to be the fraction of Ti minus that is routed to link ij, and phi ij plus to be the fraction of Ti plus that is routed to ij. As a special case, we use phi I0 minus to be the fraction that is put in computation. So this perspective of flow fractions is first used by Gallagher in a pure routing case. And we use it because it naturally supports a distributed implementation. Now let's have a closer view. Here we have a node I and two neighbors J and K. We assume that within node I there are two virtual routers, one for the data flow and one for the result flow, and there is also a computation unit. Now first, the total data flow rate T minus is the sum of the input R and all the ingoing F minus, and this T minus is put into the data router, and the fraction of phi minus ik is routed to node K, and the fraction of phi minus I0 is put into the local computation unit. So constraint here is the sum of all these phi minus variables should be 1, meaning that all the data flows must be either computed or forwarded to a nearby node. Now similarly, the Ti plus contains all the ingoing F plus and the result generated at node I itself, right, which is AM times Gi. And this Ti plus is put into the result router, and the fraction of phi ik plus is routed to node K. So the constraint here is slightly different. Right? The sum of all phi plus should be 1 if node I is not the destination. However, if node I is the destination, this sum should be 0, meaning all these phi plus should be 0. Now we can formulate our problem. Right? Our goal is to minimize the network-wide total cost T over the fraction variables phi. Now this total cost consists of two parts. First is the transmission cost. Here this big Fij is the total flow rate on link ij, and Dij is an increasing and convex cost function. Now this contains the linear cost that used in many previous works. It contains the hard link capacity cost, link capacity constraint, like the flow cannot exceed some maximum amount. It also contains most nonlinear congestion-dependent costs. And for example, if we use this Fij over mu ij Fij, we have the average queuing delay in an MM1 queue with service rate mu ij. Now the second part is the computation cost. Here big GI is the total computation workload at I, and it is the sum of all these small GIs, but weighted by WRM. Now this represents the unit workload of type I at node I, and because nodes may have different capabilities in different computation types. And the computation cost function Ci is also increasing and convex. So note that this problem is not a convex problem, but I'll explain how we solved it globally. Now we start with the KKT condition. Now this condition essentially says that for a link ij, the phi of this link can be positive only if it has the lowest partial derivative among all possible directions. Right, this is a fairly simple condition. However, it is only a necessary condition. We give an example in the paper where this condition does strictly worse than the optimal. And the intuition is that when you have t minus and t plus equals 0, meaning no flow is going through, these partial derivatives is always 0. So the condition is always hold, regardless of what the phi is. However, this non-sufficiency can be overcome if we apply a slight modification, which leads to this sufficiency condition. Now basically the partial derivative is replaced by this delta ij. We don't have time to go into the detail, but the practical meaning of this delta ij is simply the marginal cost if we increase unit flow on ij. And this modified condition is now sufficient for the global optimality, and this is our primary theoretical conclusion. And it also leads to distributed implementation because each node only needs to take care of its own phi variables and just forward the flows to the directions with the minimum marginal cost. Next, we introduce the algorithm that converges to the sufficiency condition. We use a modified scaled gradient projection, and the idea is just to decrease these phi from non-optimal links and add the amount to the optimal links. But more importantly, a carefully designed scaling matrix is used. This matrix is a diagonal matrix that upper bounds the Hessian inverse, and it is easy to compute in a distributed manner. So using this matrix, we have a fast convergence while guarantees the convergence from any initial point. Now here's the algorithm, but we don't go into the detail here. We have everything explained clearly in the paper, so please refer to the paper if you're interested. Here is the convergence theorem, and I want to point out that some feature of our algorithm that makes it handy and reliable. First, as we said, this algorithm is distributed, and the information that a node needs to update its variable could be measured and piggybacked with the data and result packets themselves. And second, the algorithm is adaptive in the change of input rates, cost functions, and network topology. And third, the algorithm allows nodes to update their variables in an asynchronous manner. Now we tested our algorithm in different network scenarios listed in this table. And the tested network has up to 100 nodes and 120 tasks. And we tested for different cost functions, including the convex queuing delay cost and a linear cost. Now here are some of the tested topologies, and we compare our algorithm with other methods here, including a non-scale version of SGP, including the shortest path plus optimal offloading, including local computation plus optimal routing, and including LPR, linear programming rounded. Now LPR is also a joint optimization for routing and offloading in arbitrary network topology, but it does not consider the congestion. Now this figure shows the normalized total cost in each scenario using each method. We could see that our SGP performs on average like 30% better than LPR. Now, if we look at the last two cases, SW linear and SWQ, they have the identical setting except one with linear cost and one with the queuing delay cost. Now you can see that the advantage of SGP is much larger with this non-linear congestion-dependent cost. Now we also have a more refined test on this left scenario, which has 20 nodes and with four major servers. The size of each node represents its computation capability. Now we remove node S1 in the middle of the simulation, and you can see that both GP and SGP adapt to the topology change, but SGP converge much faster due to the scaling matrix that we use. Now next, in the left figure, we kept everything fixed, but scale all the input rate RIDM with a same factor. Now as this factor getting larger, the network becomes more congested, and SGP is more resilient to this congested network environment. And on the right hand, we plotted the average number of traveled hops of the data packets, which is blue, and of the result packets in red. Now we compare this average hop number against the data result size conversion ratio AM. So as you can see, when AM is small, the data hop is much smaller than the result hops, implying most of the computation is done near the data sources, right? However, as AM getting larger, the network has to consider the cost of transmitting the results. So it gradually moves the computation sites nearer to the destinations. In other words, SGP does is somehow it optimizes the trade-off between the computation cost and transmission cost. So to conclude this paper, we have a novel and general model, we have a strong theoretical result, and we have a distributed implementation with promising performance. You can see that our method better supports the computation network in the coming futures. And that's all I want to present today. Thank you for your time.